In the final couple of sections of this chapter, we're really talking about actually chapter 17. We're going to talk about a special case scenario of KSP. This is solubility product and precipitation. So what happens when I dissolve a salt in, generally it's in water. So it's still going to be all of the same equilibrium, all the same concepts we've been using. I'm just applying them to a specific type of reaction that's going to change some things a little bit. So again, the KSP is defined as a solubility product. It is the equilibrium constant for the reaction of a salt in solid state, dissolving and dissociated when added to water. Now, in these problems, it's not going to give you a reaction, but you can write the reaction. This is the same dissociation reaction we write when we do net ionic equation. You have the salt is the solid, and that will be my reactant, and it's going to form cations and anions. I identify those ions, and the coefficient would be basically what the subscript was, right? So just like in net ionic equations, I would, as I figure out how many cations I have, they're no longer bound to each other, so now it becomes a coefficient. And then I can write the KSP expression. It's always going to take the same form. Remember, solids don't appear in a K expression. So my reactants, I'm not going to have any reactants. I will only have products, and my products will be whatever the concentration of the cation is raised to C, the coefficient of the cation, times the concentration of the anion raised to the power A, whatever the subscript of A was. So it's the coefficient of it in the net ionic equation, but also it comes from being the coefficients. So I can kind of take a little shortcut and just write the KSP expression from it by identifying the cations and the anions. Molar solubility is related to this. The solubility of a compound in units of moles per liter. So if I can establish what is the equilibrium concentration, and now I think about that in terms of the moles per liter of the reactant, which is a solid, I can calculate this. So if I assume that initially only the solid compound exists, so there's no ion products from dissociation, I can calculate from the KSP expression in terms of X what the equilibrium concentrations are, which is how much X is, how many moles of the substance dissolved. And then I could determine that as the molar solubility. So it's a little bit different because I'm calculating not the equilibrium concentrations, but more X, how much changed, how much dissolved. And from X, I can determine the solubility. So problems might look like this. What is the molar solubility of lead chloride solid if its KXP is 1.17 times 10 to the negative 5? I'm going to write the dissociation equation, because how can I write a KSP unless I have the equation? Again, from net ionic equations, we know we start with PbCl2 solid. That would be my reactant. Its cation is lead. I can use some math to figure out lead has to be +2 in this particular compound. So it's lead 2 ions, plus, because I have 2 chloride ions, it'll be 2 Cl- ions. Now I can write the KSP. There is no denominator because it's solid, but for my products, it's the concentration of lead ion, 2 + 2 ion, times the concentration of chloride ion squared. Okay, now I'm going to use an ice table, but it turns out all of the math is going to be related. So even though I don't really have an initial concentration for PbCl2, I can still talk about X moles of however many I started are dissolving. So I can put a negative X here, and I don't really need it for the math, but I need it because conceptually, this is what I'm looking for when I'm looking for molar solubility. So I would start with 0 of both products because I initially put this in water. There is hasn't dissociated yet. So 0 initially. I would have a plus X for lead since there's only one of them, but I'd have a plus 2X for chlorine because there's 2 of them. So when I'm done, when this finishes and reaches equilibrium, the concentration or the number of moles of lead ion would be X and the number of moles of Cl ion would be 2X. I can go back and plug these equilibrium expressions in terms of moles into the original KSP. So I have 1.17 equals times 10 to the negative 5. That's my KSP value. I can put that in there. It's going to be equal to X for the lead plus 2X squared for the chlorine. Notice that when I'm done, I have to expand this out. I get 4X cubed. So I divide by 4, and then I would have x cubed, and then I'm going to take the cube root of whatever this result is, and I get 0.0143 molar. So because I solved it in terms of what these would be, however, I can go back and say, but if this is minus x, then that means this much of that dissolves, so it's going to be whatever x is. So it is the x in the ice table because of the relationship of, if I know the equilibrium concentrations of the products in terms of x, that's what it's always going to be for how much the initial reactant dissolved. What is the molar solubility? A similar concept related to this is evaluating, will something precipitate or not? So precipitate, if I think about it, means the ions are recombining and making solid. But if I go back to what is the reaction is a solid making ions. So precipitation means that the reverse reaction is happening. The reverse reaction will happen when Q is greater than K. So when Q exceeds K, now it has to go into the reverse direction to reach equilibrium. That's when I'm going to have precipitation. So the goal, if it's asking you about precipitation, you are going to calculate Q from the values given to you. And then from the KSP expression, you write a QSP expression and calculate what is the value of Q based off of the ion concentrations. If Q is greater than K, in this terms KSP, the mixture will perform a precipitate. If it's less than K, it will not perform a precipitate. So it's a similar concept, but I'm actually looking for something slightly different. But I'm still using the K and the Q and the QSP and the KSP values and the equilibrium concentrations to determine the answer. Similar, and we won't get into this too much, is this concept of relative solubility. So I'm looking for things that, so if I have a compound and I want to consider its solubility, it changes whether I'm putting it into pure water or whether I'm putting it into water that already has some ions. In particular, if it has some ions that are either the anion or the cation, that means that I already have some initial ions present. And that's going to change and cause the Q value to increase. So it can reach the equilibrium with less moles of compound dissolved. In other words, if I want to dissolve something like lead chloride, and I figure out how much of it can dissolve, if instead of putting it into water, I put it into a salt solution that already has Cl- ions in it, it's going to reduce the solubility of lead chloride in that. And so sometimes those can be conceptual problems that are related, and it's still related to the concept of KSP.